We'll take a closer look at the heat transfer between the fluid in the pipes and the surrounding ground. As we saw in module 1.2, this was calculated as a thermal resistance between the fluid and the ground, because in that way we can include all kinds of different processes like the fluid flow in the pipes, the pipe resistance itself, interaction between the pipes, and interactions that occur in the borehole itself. Again, the question is, how can we define this for the different type of horizontal heat exchangers? And here we especially need to consider the fact that the pipes are not straight, but that for the ring collector and earth basket, the pipes are curved. So for a horizontal straight heat exchanger, the theory is basically the same as for a vertical borehole heat exchanger, but for the ring and slinky and earth basket heat exchangers, they are different. Basically, the thermal resistance gives us the fluid temperature, and it depends on different things. The water, the fluid flow in the pipe, the heat transfer in the fluid depends to a large extent on what's called the Nusselt number, which gives us the ratio between the total heat transfer and conductive heat transfer compared to convective heat transfer. And important here is the transition between laminar flow and turbulent flow. At laminar flow, we mainly have conductive heat exchange, and at turbulent flow, we mainly have convective heat exchange. So at laminar flow, we have a high thermal resistance, and at turbulent flow, we have a low thermal resistance. We can explain this if we consider the fact that the thermal conductivity of water is around 0.45 watts per meter Kelvin. So if we have laminar flow and the water particles all flow in a straight path with perpendicular heat transfer, the fluid actually acts as a kind of insulation, and it is difficult to get the heat into the pipe, which means a high thermal resistance. At turbulent flow, all the fluid in the pipe is fully mixed. Now, the thermal conductivity of water doesn't change. That's still about 0.45 watts per meter Kelvin. But as it is fully mixed, there is no conductive heat exchange, no conductive heat transfer, but convective heat transfer, and the thermal conductivity of water does not play a role anymore. So we have a low thermal resistance. Important, therefore, is the transition between laminar and turbulent flow. For a straight pipe, this is usually set at a Reynolds number of 2300. For curved pipes, the critical Reynolds number, the Reynolds number at which the transition from laminar to turbulent flow occurs, depends on the pipe diameter and the ring diameter. And we have a little formula for that with a little d and the big D, where the little d is the pipe diameter and the big D is the ring diameter. And then if we calculate for different pipe diameters and different ring diameters in the graph what the critical Reynolds number is, we can see that this varies from around, let's say, 2800 to 4000 or a bit higher for a small ring diameter. So the smaller the ring diameter, the higher the flow rate needs to be to get a turbulent flow regime. Fortunately, the Nusselt number calculation is also different, so the effect of laminar flow for a ring type heat exchanger is smaller than for a straight line heat exchanger. Another important calculation is the pressure drop calculation. Again, the pressure drop depends on the pipe configuration and whether it is straight or whether it is a ring form, and it depends also on the laminar and turbulent flow conditions. We use the fanning friction number, so the delta P, the pressure drop, is calculated as a function of F, the fanning friction number, with the density of the fluid, the length of the pipe, the velocity of the fluid flow, and the hydraulic diameter of the pipe, which is given in the formula to the right. And then we can see that for a straight pipe, the friction factor at laminar flow is 16 divided by Reynolds. For turbulent flow, it becomes more complicated, and we need different methods to calculate this. But with the fanning friction number, it is a function of a ratio between 0.0791 divided by the Reynolds number. If we look at a ring type configuration for laminar flow, the friction number is given by the formula that is depicted there, 0.55 plus 0.097 times the square root of the D number. And for turbulent flow, we have a slightly different formula where again we have the Reynolds number, and in this case we have the ratio between the pipe diameter and the ring diameter. And the D number is the Reynolds times the square root of the pipe diameter and the ring diameter. So with these equations, it's fairly straightforward to calculate the pressure drop in a system, which helps us to select the correct pump. So key points for the thermal resistance and pressure drop are the fluid properties, the conductivity, heat capacity, density, but especially the viscosity changes by the type of fluid that we use, antifreeze or water. And for antifreeze, very important is the mixing ratio, 30%, 15% or 40%, and the temperature. The temperature at low temperature, obviously the viscosity is higher than at high temperature. The pipe dimensions and shape are important, and the fluid flow velocity and the turbulent to laminar transition, which is usually calculated as a quite sharp boundary. We see that in the graph on the right for a straight pipe where at a Reynolds number of 2300, there is a very sharp boundary. This affects both the thermal resistance calculation and the pressure drop calculation. In fact, often there will be a much smoother transition like the blue line indicated in the graph because the pipe is not completely straight. There are, let's say, already turbulent puffs at lower Reynolds numbers, and then it will take some time before full turbulent flow is achieved over the whole length of the pipe. So we have to consider this in our designs, especially when we're working very close to the critical Reynolds number. Design methods are available. To be honest, the only design program for horizontal and ring collectors that I know of is a program from Oklahoma State University. It's called GLHE Pro. There are other methods like the VDI, the German VDI guideline, the 4640, that gives, let's say, analytical and tabled values for horizontal and ring collectors, or the ASHRAEA, the United States norm and handbook RP 1674, again giving analytical or tabled values that can be used for the design of these type of systems. So here some selected publications if you want to know more about this subject. And with that, I come to the end of the presentation about horizontal heat exchanger design methodologies.